Geoffrey's contribution. The floor is yours.
Oh, thank you, Sheldon. Thank you so much. Hello, it's me. And it's gravity waves and quantum jelly. And with any luck, the slides will correspond to what I have to say, all is uncertain. Last year I had the great pleasure of talking to you about rotation, and this is essentially a continuation of that. Last time I was talking about the way quantum jelly actually provided the data against which rotation could be measured. This time I'm going a stage further to consider whether quantum jelly, which I love very much, might help us to understand gravity waves and the means by which they are transmitted, and incidentally might form a structure for the universe as an alternative to space-time. It's in 3 bits, so it's 3 easy stages. I shall talk about the theoretical predictions of gravity waves. This is a hysterical thing, but I think is relevant. I shall then talk about the LIGO achievement. There's been a good deal of publicity on this recently. The detection of gravity waves for the first time, direct detection rather than just deduction indirectly. And then I'll have a go at the quantum jelly explanation. And each one will take me about 20 minutes, or if I accelerate it, a quarter of an hour. And with any luck, there'll be a few minutes left over for questions, provided I can have a fairly lenient treatment from the channel. Okay, let's take this in easy stages. Minkowski, space and time, you're all familiar with this. I've given you a reference to this particular paper, which was an address delivered in 1908, of all things, to the German natural scientists and physicians at Cologne, 1908. Minkowski, who obviously wasn't impeded by too much sense of humility, said, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Well, I don't know about you, but reading a railway timetable these days, it's about time, it isn't about space-time, so there isn't this kind of union that he predicted, but nonetheless, space-time is central to the whole concept of gravity waves, and that formed a brick in the wall for Einstein. I have a copy of that paper if one is interested in English translation. 1911, we have Einstein, a famous paper on the influence of gravitation on the propagation of light. It was translated from über den Einfluss der Schwerkraft und die Ausbreitung des Lichtes im Raum der Physik 35. And what Einstein did was to consider what happens when light crosses from one gravitational potential to another. He deduced this very simple and important formula here, where c is the final speed of light, c naught is the initial speed of light, and phi is the gravitational potential, the difference between the 2 locations divided by c squared. And that's what he put into his paper. And that, I think, is what has been quoted in later experiments. Even more famous, the 1916 paper, The Foundation of the General Theory of Relativity. This was published in German as well. I have the English translation. Die Grundlage der allgemeinen Relativitätstheorie in allen der Physik 49. From the space-time continuum and the use of tensors, Einstein calculates that an increase of gravitational potential causes the shortening of rods and the dilation of time. Predictions were given as to the bending of light by the Sun and the precession of the orbit of the planet Mercury, slightly different from the predictions given in the earlier paper. And the important remark was made by Einstein that he accepts that, quote, the principle of the constancy of the velocity of light in vacuum must be modified. A plonking statement I'll refer to later. In 1916 also, he produced a less well-known paper, and I do not have a copy of this, but I'm quoting from papers that research into the sequence of papers produced by Einstein into gravitational papers. I can give you copies of those if anyone wants to study that. So it's translated, again, I won't read that reference, and using an analogy from electromagnetic radiation. Now that's important, because what Einstein relied quite extensively on saying, well, this is how Maxwell works, and gravitation ought to work the same sort of way. And a weak field approximation, he managed to predict the existence of plane gravity waves. By plane I understand pressure waves, longitudinal waves, travelling at the speed of light. However, the approximation he used was later shown to contain a serious error, which after a few perturbations he had to correct. Followed by 1918 on gravitational waves. This is also in German. And the weak field approximation he used earlier was abandoned. He managed some exact solutions to the field equations of general relativity, still relied upon the electromagnetic. I used just EM there for electromagnetic analogy, yielding a quadrupole formula. That's very important. And throughout the rest of the study of gravitational waves, it's accepted that a dipole moment will not do. It won't generate gravitational waves. You have to have a quadrupole moment, as might be generated, for example, by a binary star system with a pair rotating around each other. Such waves were weak, proportional to V over C to the power 5, so V is pretty tiny compared with C. That's very tiny indeed, and transverse this time, not longitudinal. 1936, Einstein has now moved to America, Princeton, and publishes in English. And his paper, together with Rosen, a very talented man who was his assistant, submitted a paper to the Physical Review. Do gravitational waves exist? And he calculated exact solutions to the non-linear field equations of general relativity and encountered multiple singularities. And then concluded that gravitational waves do not exist, a view backed up in his letter to Max Born, a friend of his and a fellow well-known physicist. The editor of Physical Review referred this to anonymous referees, and the referee stated that singularities were unavoidable, gravitational waves with infinite wave fronts were therefore inevitable, and the editor of the Physical Review therefore rejected Einstein's paper. This made Einstein...
Excuse me, I'm trying to understand the logic of the referee.
I beg your pardon.
According to your story,
Yes.
Einstein showed there were singularities,
Yes.
and the referees agreed with him,
Yes.
and they rejected the paper.
They rejected the paper.
That seems irrational.
It does.
Okay.
I agree with you.
Yeah, okay. That's all I guess. Just,
Einstein thought it
very
was
strange.
irrational too. Was absolutely furious. And firstly, he thought that anybody to review his work was quite unreasonable. He was a very celebrated fire scientist. By definition, whatever he said was right. And therefore, thereafter refused to publish at the Physical Review and went instead to some other publication. 1937, Einstein and Rosen on gravitational waves. This was published in the Journal of the Franklin Institute. I've never heard of that before, but presumably it's well known to you. Acting on a suggestion from Professor Robertson, who was the referee of the 1936 paper, the singularities were removed by the device of changing the coordinates of the Euclidean space into cylindrical poles. Thus Einstein presented cylindrical waves that locally are the same as plane waves. Now he decided gravitational waves do exist.
So Physical Review didn't want to publish a paper that said gravitational waves don't exist.
They refused to publish it.
It was really about gravitational waves that they rejected. They didn't believe Einstein's conclusion that
They
gravitational
didn't believe
waves.
his conclusion, and they thought that gravitational waves did exist.
Yeah.
But
That's interesting.
if you are confused, so am I. I'll show you the paper if you like.
Go on, but don't.
Okay. 1938. Einstein, Rosen had now departed to Russia. Infeld was his new assistant. I'm not too clear who Hoffman was. The gravitational equations and the problem of motion. This was a mathematical paper published in the Annals of Mathematics. Einstein proposed a new approximation to determining the gravitational field of a moving particle by choosing a weak field and very low accelerations, and this became known as the post-Newtonian approximation. But this yielded a Newtonian particle that cannot radiate, so once more, gravitational waves are impossible. So a certain variation of view. Further theoretical work continued during the years. There's a gentleman named Dr. Hugh, 1947, who produced exact solutions and showed that that was possible. He preserved the quadrupole formula, and waves he deduced were longitudinal but very weak, and that is the basis of today's predictions for gravitational waves. That has been broadly accepted as I understand it. There have been repeated experiments for direct measurement of gravity waves. All sorts of people have hung big heavy cylinders at the bottom of coal mines and have failed to detect gravity waves. And in 1994, construction of the LIGO, Laser Interferometer Gravitational Wave Observatory, commenced, and the first version was completed in 2002. It has been modified many times subsequently, which I've mentioned there. Indirect measurement of gravity waves was conducted from 1975 onwards for some 30 years by Hulse and Taylor, a pair of astronomers. They made the first discovery of a binary neutron star system, one of which happened to be a pulsar, which was convenient because you could then measure the period very exactly. And the red dots here show how that period stiffened up as the two neutron stars collapsed slowly together due to the emission of energy via gravity waves.
May I make a comment here?
Please do.
My science teacher at school taught me but the practical results are exactly the same as the theoretical results, I must look again. Now, this one, we have a perfect fit. I haven't seen a second binary system that has this perfect fit. They all have variances, and these variances are expanding to everything else.
If you believe it's too good to be true, you're not alone. But as a historical fact, this is what was published.
I know. This is a Nobel Prize awarded for it.
I see, and there's a splendid cynicism from our chairman. And so I thought it was about time to tell you a bit more about LIGO. There are two of these animals, both of them in the United States of America. This one is by Hanford, I don't know where that is, Washington. It looks pretty arid, so I think it's probably in the rain shadow behind the Cascade Mountains. It has a central building and two arms, each a bit more than 4 kilometres long, and you'll hear more of those in a minute or two. And another one in Livingstone, Louisiana, which is almost exactly 3,000 kilometres away from the earlier one. It has exactly the same design and format, so here are the two arms, orthogonal arms. Here is a ground level, a LIGO arm, this one in Louisiana. And that's what it's like inside. This is a technician fitting a baffle, so they're quite large in a steel structure. And this slide tells us a little bit about how a LIGO works. Let's take A first of all. Here is the Washington one. Here is the Louisiana one. It's about 10 milliseconds light travel time between the two. And the two are not aligned. They are at an angle one to another. Whether that is deliberate or not, I don't know, but that is what it is.
Presumably not orthogonal to one another, are they? They're not, are they in any sense orthogonal? They're not, I think, are they?
No, sorry?
They're not set orthogonally to one another.
No, they're not.
At some arbitrary angles.
No, probably due to planning permission. There is a laser source which pumps out 20 watts, which I guess is quite a lot. A beam splitter, semi-silver mirror perhaps. So half this shoots off down that arm, half this shoots down that arm. The two heavy masses are suspended on some kind of spring system to insulate the thing from ground vibrations, ground shocks. The light, the laser light, is reflected 50 times up and down this. And I think it escapes for reasons of geometry. I don't think there's clever electronic switching. Similarly here, the whole lot is recombined here. Interference fringes shift or don't shift according to what's going on. And you can observe these and measure them there. So in essence, it's a very large and very sophisticated version of the Michelson-Morley experiment, which was conducted many, many years beforehand. This shows you the strain that is being measured, extension rate per unit length, against frequency. So you can see there are a number of spikes, there's a fair bit of noise kicking around the place. And you can identify that spike with these 60 cycle mains, which of course is what is used in the United States. But what I would point out is the extraordinarily low level of strain that can be measured using this technology. Well, we heard about 6 months ago, I guess, that the first signal had been received by LIGO, which was thought very certainly to be a gravitational wave. And here are the two raw signals shifted a bit because they weren't received coincidentally. There's a bit of a time shift between the two. So I think Hanford is in blue and Livingston is in orange, and you can see they fit pretty well. And the idea is that there are two black holes, not supermassive black holes such as you might find in the centre of a galaxy. These are common garden black holes, a few similar masses each. And so here they are rotating around one another. They merge together, they finally collapse. There's a huge emission of energy, which fortunately was a long way off, and the whole thing just subsides into noise. We see this in a bit more detail. Here is red in Hanford. Here is blue, Livingstone. These are the theoretical predictions. Those aren't the process signals, they're the theoretical predictions. And if you subtract that from that, you see the resulting noise, which can be analysed presumably for randomness. These curious diagrams are a plot of frequency against time. So you start about here at about 30 hertz, and the signal creeps up, increasing in size and volume, up to about 250 hertz, something like that. So it only lasts about 0.2 of a second. It's described as a chirp, rather like a chirp of a bird. You produce it acoustically. The LIGO data are fascinating. The bandwidth is okay. You can rely on receiving something fairly accurately between 30 and 70 kHz. Duration 0.2 seconds. Interval between receiving both signals 7 milliseconds. Now, if it were absolutely flat, it would be 10 milliseconds, so presumably it comes from up there somewhere. And doing a bit of triangulation, you can define an arc within which it has to be. The best guess is that it comes from behind the Magellanic Cloud, but that's uncertain. And when we have a third LIGO, which is due to take place in India, I gather, Australia, this is not the only success they've had. It was less widely publicised that on Boxing Day 2015, they saw another rotating pair. They had a debate, whether to save electricity, would they turn the LIGO off over Christmas, and they decided not to, so they got a Christmas present on Boxing Day. Here it is. This is the noise, this is the raw received signal. After analysis, it was possible to produce this. Two different merging black holes, 14.2, 7.5 solar masses. They merged together here with a big burst of energy. I'm very interested in the profile of this signal because it looks to me as though we're looking at a spot of quantization here. And the quantization of gravitational potential, I think, is an interesting subject. But anyway, a second success was scored. So where do we get to? Conclusion so far. Not just one, but two sets of gravitational waves were observed. Both match closely waves predicted to result from a black hole binary system about to merge. Also, we have the Hulson-Taylor observations of binary neutron star system show gradual loss of energy exactly as predicted by GR theory on gravitational waves. Gain, set and match for general relativity and gravity waves. Or is it? Question mark. This gets me to my third spot. So I'll wind up and stay silent in about 20 minutes' time. Is that okay? This will be... I found this in the pack of illustrations issued for publicity purposes by LIGO. So that's their own views. I like that very much. Okay, let me give you a bit of background to quantum jelly. I've been talking about this for a long time, so I'll whiz through.
Before you start, can I ask you a question? Now, the history is that the LIGO staff made the publicity and said we have observed gravity waves.
They did, yes, they were very
So
firm
they
about
weren't
that.
sticking their heads in the sand, were they?
Why were they
They
sticking
came
their
out
heads in
and
the
said, we did it.
Well, but why do they make a point of including that illustration in their publicity pack?
Well, I don't know. I don't know. Right.
Yes.
How do you understand?
Yeah.
How do you interpret it? What do they say?
Oh, Lou is absolutely right. The headlines, the press release was absolutely triumphant.
Yeah.
No, we have succeeded.
So why are they showing themselves with their heads in the sand? I'm too stupid to understand. I want an
They
explanation.
want to do more research.
I'm sure
That's
they
for
do.
sure.
Or maybe they weren't. Maybe they weren't quite so certain.
Yes.
Maybe they were friends of ANPA.
Otherwise, you might just finish the project. You want some.
So they were being humble and saying, well, who knows?
Yes.
Well, it's a well-known American. I mean, humility is a well-known American characteristic. So what am I talking about? The fundamental thought that worries me is the universe a digital system? And in case anyone is going to accuse me of just making up picking up what a digital system is, what I mean by that is that it is a system which is capable of accepting a digital signal or a digital variable operating on it by a second to produce a third. That's what I mean. A consequence of that, if you say if this then what, all variables are quantized in one way or another, and incidentally have maximum and minimum values. I could answer questions on that if you wanted me to. Particles with half-integral spin, I do hate that term spin. Translation from the original Greek is swerve, I think that is a much better term. Have extended probability-based structures whose interactions explain action at a distance. No fields needed. Charge can be explained in terms of angular momentum, which is why I'd love to ask Peter a question about charge, but later.
I think you probably asked me that before.
Oh, in that case...
And I think I gave you an answer, which I think sounds funny, but ask me again anyway.
Treat for after lunch.
I just thought to mention it's Banesh Hoffman.
Yes.
That's the name of it.
Thank you.
Banesh.
Oh, thank you.
If you're looking.
Such structures combine to form not quantum soup. Now all physicists know and rejoice in quantum soup, but quantum jelly. In other words, a quasi-solid which can vibrate and transmit waves among two other things. And that is one reason I was particularly interested in your paper this morning, because I think that to describe quantum jelly where the particles are, shall we say, virtual, they flash in and out of existence, I think we may have to resort to imaginaries there, and I think that that is something I can probably understand better in the light of your paper. That transmit waves, and it can make it, just like an earthquake, transmit transverse and longitudinal waves, and comes mostly from the outermost reaches of the universe. I better explain that quickly. If you have an electron here, mean position, occasionally it's going to be here, and the chance that it's there is proportional inversely to the distance between them. So, the further away you are in the universe, the bigger the contribution here. The probability decreases as 1 over r, but the volume of the shell increases as r squared. So in this chunk of space, most of it comes from the outermost reaches of the universe. Which is why, by the way, that the datum for rotation is defined by the outermost reaches of the universe. I thought you ought to know that. Is quantum jelly the structure of space? Quantum jelly is insensitive to relative velocity. I better explain that. If you have particles that are flashing in and out of existence, you can't measure your velocity relative to these, particularly if it's legitimate mathematically to describe them as imaginary. Which means that the argument that was cited all those years ago, there is no ether wind, therefore ether doesn't exist, is not compelling. The alternative is that there is an ether, but it just isn't sensitive to relative velocity. Which means that quantum jelly, this curious quasi-structure made up of imaginary particles, could be the ether that transmits electromagnetic radiation. Also, it is certain that electromagnetic longitudinal waves exist. Plenty of publications from Russia, central Mexico, because they have military significance, because they have very high penetration, which means you're not protected if you sit in the middle of a tank. These things are not widely talked about in the Western world, but there's very little doubt that longitudinal electromagnetic waves do exist. The papers are available, you can read about it. So the concept of electromagnetic fields becomes doubtful because Maxwell says that these things are not possible. If you want to use Maxwell's equations to justify the existence of longitudinal EM waves, you have to invent more terms. And as Einstein will agree, that can be a dodgy thing to do, it can find you out. I'm thinking of the constant that he popped into his equations. So, as the outermost reaches of the universe set the datum against which rotation is measured, I mentioned that just now, quantum jelly may be the means of such measuring. In short, quantum jelly may be the means whereby space has a structure and electromagnetic waves are transmitted. So the question is posed, are gravity waves therefore transmitted by quantum jelly, not by space-time? Now, it'll take me just 2 minutes to transfer to the next bit. Okay, gravity waves and quantum jelly part 2. I apologise for the break, but I ran out of memory at this point. How fast is gravity? We've had a discussion with ANPA before. Peter, I think you're adamant that gravity is instantaneous.
Yes, static gravity.
Yeah, it's an important point. I agree with you. LIGO shows very definitely that gravity waves travel at some speed.
Yes.
So gravity has to be instantaneous. If not, Kepler's laws don't work. I think that's simple. Gravity waves have a finite speed, see LIGO data, claimed to be the speed of light. 1. Can instantaneous gravity be reconciled with gravity waves that travel at c? And 2, does it make sense that there are 2 different media, one for transmitting gravity waves, space-time, and the other for transmitting electromagnetic waves? Could one medium suffice for both? Couple of questions. Let's address the first one first. QJ consists of virtual particles that are extended structures of distant real particles. If a real particle moves, its structure of virtual particles moves with it, identically and instantaneously. In other words, it doesn't take time for gravity to travel from the Sun to Jupiter. It's all part of the extended structure of the particles within the Sun, and it travels, it's there instantaneously because it's already there. Chairman, suppose you had a great friend who is a jellyfish. And this jellyfish has long extended tentacles that dangle into the ocean. His technical name is a Portuguese man of war, soon to be rechristened a European man of war, I don't know. And suppose you were swimming next door and you were stung by Joseph. And he would say, I'm terribly sorry, old chap, I'll move out of the way, and he would sort of scoot off from the altar, and his tentacles would go with him. The jellyfish is just like gravity. His extended tentacles travel with him. But suppose Joseph turns around in this shoal of jellyfish. If shoal is the collective term for jellyfish, I don't know. And he sees his friend Agnes. He says, Agnes, do you know what? I've just stung our chairman. And Agnes says, oh, that's awful, I'll tell the girls. And the news filters through this shoal of jellyfish. And that's what gravity waves are like. They travel between collections of vertical particles, quantum jelly. It is the wave that travels through quantum jelly. So your summary, I think, Peter, has my vote. It's absolutely precise and accurate. That's what's going on. Okay. Question 2. Mechanical waves are transmitted in the Earth's crust at different speeds according to the type of medium and the type of wave. In other words, pressure waves travel faster than transverse waves. And if you're going through limestone, it's a bit different to going through granite. So if you're a geological surveyor and you blast off an explosion and you time how long the waves get to you over here, you have a pretty good idea of A, what sort of wave it is, and B, what it's been going through. So the speed of wave is normally sufficient to determine both types, the type of wave and the type of medium. If electromagnetic and gravity waves both travel at sea in vacuum, and that's what's claimed, the medium of one is probably the same as that for the other, and the two waves are likely to be of the same type. So, since we are told with great firmness and authority that gravity waves travel at sea, it's highly likely that they are travelling in the same medium as electromagnetic waves. I don't know of any other medium that will transmit waves at sea. Maybe you do, I don't. So, quantum jelly, if it is the medium, I can't see any alternative to that for transmitting EM waves, it's probably the medium for transmitting gravity waves as well, on that argument. What about these longitudinal waves? But gravity waves are very low frequency transverse EM waves is unlikely, because gravity waves penetrate deeply, which EM waves, transverse waves, do not. Normal electromagnetic radiation is stopped by a Faraday cage, and yet the gravity waves penetrate through this steel cylinder and allegedly compress space-time and give you measurements on LIGO. They penetrate deeply. Therefore, it's suggested that gravity waves are longitudinal EM waves, which strikes an echo, strikes chords with what you've just been saying about there being two different bits. You don't see longitudinal gravitational waves. Our eyes only see transverse waves, which accords with Einstein's final view that such waves are plane waves and explains their extraordinary powers of penetration. The speed of such waves is likely to be similar to C, but probably a bit faster. I have no idea what Poisson's ratio is going to be for quantum jelly, but it will make the speed of transverse waves, which we measure very precisely, a bit different from the speed of longitudinal waves. Tesla, who knew all about longitudinal EM waves, speculated that they were just a little bit faster than C. Later workers say it's 1.5 times faster, is nearer the mark. We're honestly not sure, but it's fairly close to C, that much is sure. Is C a constant? When I was a student, which was a very long time ago, the answer based on special relativity was unqualified yes. You know, we were told that C, wherever you were, whatever you did, was a constant. That's in vacuum. Today, answers are less certain and reflect Einstein's remark of 1960. He knew all about it. Experimental physicists, principally Dr. Owen Shapiro, have measured that C varies with gravitational potential and is not constant, a fact still contested in some quarters. Though it is widely accepted because he got a very prestigious prize for this particular work and a fairly large sum of money as well.
Can I ask, is there a distinction between the second and third case, the Einstein stuff and the Shapiro stuff? Are they distinct in any sense? Or are they really saying the same thing?
That's just what I'm going to come on to. The short answer is yes.
Oh, there is a distinction.
No, the
Oh,
short
they are
answer is
saying
I'll say the same thing.
Oh, thanks.
Right. What Dr. Shapiro did was marvellous. He persuaded the American military to donate a very powerful transmitter of radar waves to MIT, and he shot a beam first of all, as a planet, Venus, as it just skirted the Sun, so you had to pick the orbit rather carefully, got a reflection back and could measure how this varied as you approached the Sun and as you swept past it. And the answer was you got this very beautiful cusp, and you can see the straight theoretical line predicted and the measurements which sit upon that. And this shows you what he did later, because the Mariner 6 and Mariner 7 probes rotated around Mars, and they were transponders. So as the orbit of Mars skirted the Sun, you could send a pulse which could be transmitted back very efficiently and very promptly by the probe, and that allowed much more precise readings to be made. So this, I think, is responder data, and that, I think, is the earlier response from planets. And again, a very beautiful cusp, and you can see the error estimations on the various readings and how well they fit. Now, the important point here, I think, is that this. If you take the predictions from space-time, using that as a medium for the structure of the universe, you are told that variations in gravitational potential will give you shortening of rods, and dilation of time. If you're taking quantum jelly as your medium, as you skirt by a heavy body, for example the Sun, the speed of light will change. The speed is determined by the square root of Young's modulus divided by the density. So the output that you measure is not a shortening of rods, it is a variation in the speed. And that gives you the same answer, provided the equipment is designed to measure it and provided the variation in speed is small. Now, to come on to your point, if I may, Shapiro took the model put forward in Einstein's earlier paper, the 1911 paper, that the speed is variable by phi over c squared. And that is contradicted, I think, in the later paper, because there the rod will shorten if it is along the radius. Here you are, here's the Sun, there's the radius. If it's tangential, the rod does not shorten, which means that the speed tangentially is different. You do get a variation in speed, but it's different from the speed if you're going in that direction. The fit here is beautiful. It's based on the assumption that the speed is isotropic, the speed differential. There's no preferred orientation, it is the same. If you took the predictions of space-time, as outlined in the 16 paper, I think you would get a poorer fit. So summary, what am I trying to say? Am I in scope on time?
Perfectly.
Okay. I'm saying electrons have extended structures. Such structures explain electromagnetic action at a distance. Also the fringes from single electrons aim at bioslits and all sorts of other things as well. Imagine you've got a truth meter, sort of a swinging needle, and you could plug this into a hypothesis and the thing would tell you the probability that it was right or not. If I had my truth meter and I plugged that in, I would say to me it's about 50% likely to be true. Extended structures form quantum jelly. It's obvious that equally charged constrained particles will form a lattice, and I've even shown you previously my little model where the little charged beads constrained in a box form a nice little lattice, and you give them a shake and they can wobble a bit so they can transmit waves. I give that less, that's about 30% likely to be true, but it's still a possibility that hasn't been discounted. QJ defines the structure of the universe. If not QJ, then what? QJ has substance, space-time does not. I'm uncomfortable with the thought that you can define a structure without there being some form of substance there. And I doubt very much whether fields really do exist. I suspect that they are all just models representing when the extended structures of particles interact between each other. Detemporization is extremities of the CQ, and QJ is the only known means of conveying such information instantaneously. That fact, I think, is another indicator that QJ might be the structure of the universe. On my truth meter, I think that's about the 50% mark. Sorry, 30% mark. QJ is the medium, the ether for EM waves, both transverse and longitudinal. I think we have to abandon Maxwell. Quantum jelly is insensitive to relative velocity, I've said that before, so no ether winds. Longitudinal EM waves exist, see Tesla, but are forbidden by Maxwell. I think that's probably about the 50% mark. The speed of light is not constant and varies with change of phi. I think that's 100%. I don't think that can be argued with. Wherever you are, if you have a little piece of experimental equipment that measures the speed of light, it might be a cesium clock that goes between the water tower here and down here. You will get a change. The speed of light is not constant. Gravity waves exist, I'm sure they do. Such waves travel about C and are penetrating. So that means they must be longitudinal, they can't be transverse, and they travel via an ether, which is QJ. Give that sort of 20%, something like that. So I'm aware that I'm talking about some very fundamental issues. I'm aware that one needs to approach these with considerable objectivity and humility. A large part of my so-called career was spent as on the board of directors of a venture capital company, and I was sitting on the other side of the table telling eager and enthusiastic applicants why their ideas were no good and weren't worth investing in. And I'm now on the other side of the desk. Here am I, an enthusiastic young amateur, proposing various outrageous thoughts. Well, I may be wrong. I really may be wrong. But if I'm not, there are a good many textbooks that will have to be revised. Thank you, Chairman.
Terminology. You've come across scalar waves.
Yes.
Are they, in the normal sense, just rename the longitudinal?
Not entirely, no. I'm talking about your bog standard compression wave,
Okay.
like that.
Right.
Not a derivation of cylindrical polar waves or...
No, I mean there's the word scalar waves or the term scalar waves.
There are all
It's got
sorts
about
of waves.
87 meanings,
There are
right?
soliton waves and surface waves and all that stuff. I'm talking about the longitudinal wave, such as might be transmitted in an earthquake.
The second thing, Maxwell didn't do the bad things.
So
Maxwell didn't leave out what you call longitudinal waves. The people following him decided to leave some terms out of the rather complicated way. He's still a good guy.
Maxwell is no taught, needs revision.
It was early stuff in the mid-1800s, right?
Yeah.
Yes, Nina. Okay. 2 points. One has to do with Peter's paper.
Yes.
So the point is, the structure, you said the structure of the universe must have substance.
Yes.
And here I am addressing both of you. So space-time, it's without substance, according to your view. So can it be the substance given by the double space Peter was talking about? Because then he said physics and maths have the same structure.
What Peter said was the reason I woke up while he was giving his lecture. I think there really is something to be explored here. And the substance I'm proposing is pretty funny stuff. If we're talking about virtual particles, which mathematically can be described as imaginary particles for almost all their existence, then it's funny stuff, and whether that too can be described as being substance, I think it probably can. If it can transmit waves, I think it probably has substance, and some interesting work to be done there. Really, I think I'm on Peter's side on this one.
Okay. And the other point is just the curiosity. How do you explain the oscillation of Einstein's positions in his different papers?
I'm afraid I have no explanation
Because
at all.
on the topic of gravity waves.
It's an extraordinary piece of behaviour.
Because if I understood rightly, he said once he was saying yes, and the other paper he said no, and then he was going both ways.
Exactly. I have no explanation. It's a underpublicised aspect of Einstein's work. And I suppose it reveals that the greats are also vulnerable.
Because probably was taking into account one thing and not another.
Or a certain resistance to abandon his earlier ideas.
I see.
Roger?
Hi. Sorry. Can we go back to part one for Einstein 1913 paper, where he puts down about the equation with the phi and the c in it?
I could. It might take me a millisecond or two.
Thank you.
Let's write it down here, Mark. If we go. Let's see, equals 1 minus 5 over, was it c squared, I think? Something like that.
Give it C naught. This is C naught.
Is that the one you want?
That's it, yeah. Yeah, when I look at that equation and read it in the books, the text in the papers, it looks to me there's a printer's error, and when it's c squared, it really should be c0 squared. And also,
you know, that's such an important point.
Yeah.
You can argue it either way, I think, from the way Einstein defines it. Can I give you his original paper and you can have a look?
if you, yeah, if you.
It just so happens.
It looks like there's a printer's error in there.
No, it's not.
It's not a printer's error.
No, it's not.
Does your quantum jelly insist that gravitational waves are quantized?
That is a really tough question. Let's assume that phi is actually gravitational potential. And that is Gm, gravitational constant multiplied by mass, over a distance. If you take my hypothesis that everything is quantized, distance will be quantized, so too will be mass. They're probably quantized very, very finely, so that you cannot observe that directly. But you can observe it indirectly, because if you divide one by the other, you then are likely to get a preferred version, a preferred value. If you divide voltage by current, you get resistance. Voltage very finely quantized, current very finely quantized, resistance 25,000 ohms. Absolutely measurable. Which is why I'm so interested in whether gravitational potential is quantized or not. take the quantum jelly solution, I'm less sure there that you will find quantization. So the existence of quantization or not might be an indication in one direction or the other. I think that's the best answer I can give you for the moment. Watch this space.
All right. I have trouble with gravity being quantized. I'd have it more be topological jelly or something else, but you made such a complex thing that it would take, an hour to discuss it. So
In which case, I think you and I are on the same side.
perhaps, probably.
Thank you.
We actually have some time on hands because it was a carry over mistake from the previous timetable that we had a talk 10 o'clock to 11 o'clock and a talk 11 o'clock to 12 o'clock and then lunchtime from 12:30 to 2:30. So you can now handle me for missing the tea.
The tea break, we missed it.
I took coffee break away. And I stopped. So, we can, I think, if there are further questions or, or going to groups like Shapiro, for instance, I actually mentioned him in the proceedings in my article. They are now using the Shapiro delay to measure the so-called reflection of light. But what they're actually doing with the transponders, they transpond two frequencies back, and then they measure the time delays of the different frequencies, and then they point out so it's a predictive correction that they do. They actually, it's about 250 microseconds, or you said 20 to Mars, but they have about an additional delay of 100 microseconds, which needs to be compensated out of it, going through the atmosphere of the sun. So, and that's what I call a predictive correction to suit the factor 4 for the reflection of light.
May I comment on that?
Yes, sir.
I think you're spot on right. And I do have papers that talk to me about the delay that could be caused by the corona of the sun.
Correct.
It has mass, it would reduce the speed of the transmission of light. Does it account for the shape? Well, you then have to do some careful calculation about how far the corona extends from the sun.
Well, nobody knows.
And as a result, there is a good deal of scepticism with regard to Shapiro, particularly those diehards who believe that C is absolutely constant and believe what they were taught at school.
Surely the corona of the sun is likely to not be, its distance from the centre of the sun is not likely to be a fixed distance.
We're talking about 1 over r rather than 1 over r squared, so it isn't a Gaussian situation. But yes, I agree with you.
I would have thought it was a fuzzy quantity.
Yes, I agree. But there are some very powerful, overstated, hysterical papers that are published from gentlemen and ladies who really don't like the idea that C is constant.
Well, my theories are based on a level of C, but we can discuss this outside your talk. Any more questions to Geoffrey? Maybe we want to use this time for either discussing among ourselves or Peter, if somebody has questions.
Why don't you get Peter back on?
Yeah, that's...
He's better at answering questions than I am.
Now, okay, before Peter comes on, Geoffrey, thank you very much. A most enlightening talk.